Okay, is it to start? Okay, recording is started. Okay, fine. So basically, this is the second unit, which basically going to tell you about what is the current. Right? Am I? What? Somebody is asking something? Okay, fine. This is the second unit, which basically having a basis of the current mode approaches basically. Okay, we're going to learn how this current mirrors are there and how current conveyors is going to be work upon, and how we are going to learn what is the basic things within this one. So for that one, what we are till now, what we are doing, whatever the circuit we have learned, that is basically depending on the voltages. Like if I say some kind of analog circuit, like say op-amp. So op-amp, it is dealing with the voltages, and output is also coming in the terms of voltages. Even in the controlling thing is also a voltage. It means everything is deal by the voltages, not the current basically. So what is that one? There is some chaos is coming when, let's say, if you want to replicate some same voltage somewhere else within the circuit, we cannot able to do. It means the voltage is going getting divided in a series wise. Okay, so that is what basically things is going to happen in that a voltage mode type of circuit. Even that there is a less, you can say a range of working is less in that one. Let's say talk about the CMOS having some kind of a 1 megahertz of the range where we can do working. Okay, we can extend this thing in the current mode circuits basically. These are a few examples, that is what I'm giving. So basically, what is current mode circuit? The, the class of the circuit whose function depend mainly on the use of the current signal, and which can be designed and understood certainly at the basic level using the method which is voltage need not to be considered in that case. Such type of circuit, nothing but called as a current mode circuit. Basically, what I'm saying, that we are basically design a circuit which basically totally depend on the currents, basically current signals. That is current signals. Okay, and why we require a current mode circuit? Because it is rapidly superseding the traditional approach based on the voltages. Superseding means it is a very quick responsive rather than the voltage mode. Second, it provides an attractive and elegant solution to many circuit and system problem by looking into that like a mirror. We have already gone through the mirror circuit. So basically, if I'm going to say the same thing, just talk about the BJT. If I'm going to connect further this BJT again somewhere else, so whatever the current is flowing through this one, it is going to flow this one. The same current will flow from this one also, this one also, this one also. Okay. It means if I'm going to extend this part, further we'll get a same thing, same current will going to get. It means in this way, we can have an elegant solution. In several places, we can replicate that same current. So we don't have an issue of the current. Same current will be there. Although biasing voltage will be remain same. I'm not saying the biasing. I'm saying about the signaling, current signaling. Okay, that is what the thing. And what are the key performance features? That is inherently, inherently wide bandwidth, means as I told you in the CMOS it is ranges from a 1 megahertz only, so it is reaching up to the gigahertz range basically. So due to that one, if bandwidth range increases, means dynamic range also going to be increased. And this similar circuit rather than the complex voltage mode circuit. Like if I'm going to talk about the this comparator circuit, basically instrumentation amplifier. So it required a three type of op-amp. That is a very big things is there. That is what here we are not going to face that big issues of that one. Then then it is easily cascading. That is one of the example which is given here only. Cascading is very easy. It means we are cascading, this is only, that is what the cascading only, here cascading, the same thing. Okay. And the last one is transistor is useful for FT frequency, means it is not going to deteriorate it basically. That is the basic key performance of the current mode circuit. So current mode circuit, that is basically deal with the translinear loop or the translinear network. Translinear loop, basically it is going to translate the things from one place to this place. This is what translating the current here. Translating the current here. That is what translating the current. So this is basically a translinear network and loop, basically, which I'm going to see. I'm going to tell you what does that basically mean of that one. So basically, if I'm going to say about a translinear loop, that is circuit involving one or more closed loop of the junction of the BJT, that is emitter base, basically. And translinear network, that the circuit which do not involve any closed loop of junction of BJT. Okay, here you can see there is no any kind of a loop is there. So that is basically the things of the translinear circuit. So comes to the what is translinear circuit design principle. If I'm going to see translinear circuit, this is what the translinear network, and this is a translinear circuit. Okay. So translinear circuit design principle, that is introduced first by the Gilbert in 1972. This is a principle and technique for design and processing of analog circuit and system based on the current mode approach. Okay, that is what the basic thing. Here you can see a loop is there. Okay, that is the one of the loop. And what is the basic principle? If I'm going to collect the mathematical terms, if I'm going to represent the collector current in the terms of the scale current, you're going to get IC is equal to IS exponential of VB by VT, basically, where the IC is the scale current and VB is the nothing but a base emitter voltage and VT is the thermal voltage. This is what KT by Qn, basically. This is nothing but a temperature dependent quantity. So that we need to take care of that one when we are designing some kind of a BJT circuit and all. Where the VB you can represent in the form of IC by IS through this equation only. So from equation 1, okay, sorry to forget that this part also. The principle, basically, principle I skipped this principle. So come to the principle. What is that principle behind that one? Translinear loop network. Yeah? Let there is a closed loop having NPN junction are forward by some mean. Okay. Here whatever is represented, you can see here. That is what basically a base emitter is. So where the VFK is a junction voltage, where the K ranges from 1 to N. If I'm going to aggregate the voltage at particular loop, it will nothing but a overall VB0. That is the first of the equation. Practically junction, there will usually represent base emitter junction. That is what I have told you. Hence, VFK is nothing but a VBEK. Okay. And collector current is nothing but going to be represented by ICK. Okay. That is the basically loop of that one, where based on that one we are going to collect the collector current, and from the equation 1 we can deduce that part, that is nothing but a VBE. Okay, I'm saying VBK, so I'm replacing that one and we can get the equation 3 on the basis of 1 and 2, where the ISK is nothing but a different for a different junction. It includes the possibility of different area junction, different type of NPN or PNP. Assume here we are going to assume the VT equal for the all the junctions. Then what is going to happen if I'm going to aggregate that part? Then equation 3 becomes nothing but this one, which is equal to 0, and 0 is nothing but we can represent in this form, this one. So, if I am going to equate the economic inequality, that is going to come this one. And for a practical circuit, okay, practical circuit, for any practical circuit, I C by IS, basically if I'm going to say about the IS is nothing but 10 to the power minus 18 ampere, that is the range. But if I'm going to talk about the collector current ranges in the milliamps. So it is itself, it is saying it is very higher range. So practically you can say this is IC by IS is very, very high because it is in the denominator term. So it will become, if I'm going to say like this one, IS by IS, it is nothing but a milliamp into 10 to the power 18 also will to come. It is very high quantity. So that's why it is going to be say this is very, very high. Hence, to satisfy the equation 4, the condition is to be satisfied even number of the junction in the translinear loop and equal number of CW and CCW facing junctions. Note that if NPN and PNP junction are mixed, then they should appear in opposing pair. Since their IS may have significant different temperature coefficient, as I told you, it basically depending on the temperature also, because it is nothing but a scale current. So scale current itself having so many terms which is depending on the temperature. Let's assume all the devices are at the same type. Okay. And may have a different emitter area. So different emitter area means different IS. Now from the equation 4 may be written like this one. Okay. As IS tending to emitter area, hence it good translinear practice to represent area of emitter by unit E, 2E, 3E means electron. This is nothing but electron and Ne. Hence ISK is nothing but going to become AK by JSK. JSK is nothing but current density. So if I'm going to represent in the form of this one, so we're going to get this value basically. Okay. Else ICK by AK is nothing but a emitter junction density. That is what this thing. Hence you can write this also. So statement for the translinear principle in a closed loop containing an even number of forward bias junction arranged so that there are an equal number of clockwise facing, that is clockwise facing and anti-clockwise facing polarity, then the product of the current density in a clockwise direction is equal to the product of current density in a counterclockwise direction. Oh, let's see. Now let's see the vector difference circuits. And first of all, let's see what is the vector difference circuit. Then we'll come to this equation. This is a what vector difference circuit. Okay, this is what the vector difference circuit, where the Q2, Q1, Q2, Q3, and Q4, Q5. Okay, here if I'm going to see what is that, this part is nothing but a what kind of a BJT. Okay, and here this is nothing but a current mirror. And if I'm going to look into this part also, this is also a current mirror, type of a current mirror. Okay. So what I was saying, if I am going to look into this part, this is a one kind of a current mirror. Okay. And if I'm going to look into this particular thing, this is also a current mirror, right? So that is what, and we are going to look into two parts. That is a loop, this one, that is a loop one. And if I'm going to look into this hole, that is what called as a loop two. So that is what we are going to consider first. So here the two translinear loop, loop 1 and loop 2, transistor Q2 and Q3 form current mirror, as I told you also. Hence, IC2 and IC3 are equal. That is equation 1. Applying a translinear loop at the loop 2, we'll get this equation. That is nothing but going to get this part. From this is what second equation. Okay. Here, if I'm going to look into this one, the IC2 means this part. Okay, this is IC2. So IC2 is nothing but the IY plus current coming from this thing. That is equation 3. And what is this IC1? If I'm going to look into the IC1 is nothing but IX. This is what the current is coming. Okay, and one of the current which is going in this direction. Okay, that is this one, because minimum current is going inside the base. So that is what this one, right? And this is nothing but, if I'm going to see is IC3, okay, if I'm going to see into IC3 is nothing but IC2. Okay, that's why we have written IX minus IC2. So from 3 and 4, we can write IC2, that is going to come, basically you can say a mean of IY plus IX. Now look into the equation 4 and 5. Look into the equation 4 and 5. If I'm going to write IC1 into IC2, okay, that is 4 and this one. Okay, if I'm going to look into this one, and if I'm going to multiply these two, what is going to happen basically? That is going to come like this, the IX square minus IY square by 4. That is, we are going to get this part. Now from equation 2, we can get IC4, this IC4 into IC5, this is IC5, that is nothing but a IW square. Where is the IW? This is nothing but this one. So we can write 4 IC1 IC2, since IC4 IC5 are equal to IW. Okay. So IW can be written under root of IX square minus IY square. That is the vector difference. Okay, that is what vector difference circuit. So what is the limitation? IX must be unipolar. And second one is IY may be a bipolar, but it should be under the limitation of this mod of Y is less than IX. That is what the vector difference circuit. Now comes to the diode bridge. Okay. From here we have started. So come to this point only. Now apply a translinear loop. Okay. So if I'm going to writing a 1 minus xib, 1 minus xib, okay, and into ic plus 1xb. Okay, I have not solved this thing. If I am going to if you are going to properly apply a KVL within this translinear loop, you will get this equation. Okay, I'm not going to solve this particular thing. After the solving, I have written this thing. So you go into look into that equation of the KVL and you can write it. Okay, because it will take further little bit time to write this part. So from this equation for the diode bridge, we go into another part. Now solving the above equation, we can get basically x equal to IC plus IB by IA plus 2 IB plus IC. Let's say example IA is equal to 1 milliampere, IB is equal to 2 milliampere. Here the misprinting is there. That is a milliampere, milliamps. That is a milliamps. Okay. So IA is equal to 1 milliampere, IB is equal to 2 milliampere, and IC is equal to 3 ampere. Okay. This is what the given. This and this. Okay. Then what is going to happen? If correct, then I1 into I3, I1 into I3, I1 into I3 is nothing but is equal to I2 into I4. So practically also find that LHS equal to RHS, as you can going to see into that one. That is going to come same thing. Hence the result is correct. Now comes to the translinear one quadrant squarer or divider. That is how we are going to get a squarer or the divider. It can function as a both squarer or the divider. This is how we are going to basically design the mathematical terms by using the translinear loops. So let's look into this one. Here output can be written in the form this one quadrant because both Ix and Iy is the unipolar one. Keep it in the mind. Here I am saying that Ix is a unipolar and Iy may be a bipolar. So when I am going to say about the translinear one quadrant, in that case Ix and Iy will be unipolar only. Then only the translinear one quadrant squarer or divider can be designed. Okay. So don't so much worry about the circuits because circuits are very easy. Mostly are the current mirrors. You need to look into which is current mirror, which is the current mirror. That's the things you need to check it out. So if I'm going to look into this one, this is the first current mirror which I can able to see. Okay, this is only the one thing. And here it is talking about the we are going to look into the slope basically. So I1 into I2. So I1 into I2 means the current flowing to this one and this one. It is nothing but a current through multiplication of I3 and I4. The current flowing through this one and this one. That's the mean of it. And if I say I1 is equal to I2 is equal to Ix, the same current. Okay. Then Ix is square. That is what the unipole. So Ix square is equal to Iy into Iw. Okay. So I3 we know this current. This is current nothing but Iy and I4 that is nothing Iw. So this is what if I'm going to find out this thing, this is what we are going to get for the loop value circuit. Now come to the square rooting and geometry mean. So for that one, these are the circuit basically for the case of absolute value circuit. You can see it here. If I am going to evaluate this part, you will get for the in the form of the absolute value. And when we are going to use a Darlington pair, that time this is another circuit for the absolute value circuit. This is the absolute value circuit. Okay. If I go, similarly, the same way which how we have calculated this thing, by that one applying that loop and all, you will get the same result. But simply you need to check it about that one. What is the current mirror? If you know this thing, you do need to identify which is the current mirror. Okay, here the current mirror, and here you can see the current mirror. Okay, by creating this all thing, you will get the absolute value of this one. It means IW is equal to nothing but plus minus IX. You will get the same result by solving that. Similarly, now check about the square rooting and geometry mean. Square rooting or the geometry mean. The square rooting basically, you can say if both are going to be same, then it will going to come a IX. Or if it is different, it is going to say a square root of the both of them. This is the basically circuit for the square rooting and geometry mean. So we need to look into this loop. Okay, and we need to identify the current mirrors. If it is there, that is also okay. If it is not there, then we're going to look into how it is basically performing the things. So if I'm going to apply a loop across this one, you will get the IW, this current, okay, this current to be under root of Ix into Iy, or you can say IW square is equal to Ix into Iy. Okay, that is what you are going to get. This is what square rooting and geometry mean. One of the example I have given already in the previous slide, and this is what how you are going to calculate basically. I have already given the loop where we need to do a KVL. Now comes to the vector magnitude circuit. Vector magnitude circuit. This is another example for the vector magnitude circuit. So here you need to apply a KVL. That time you will get a square root of magnitude, that is the Ix, and Iy square. That is what called basically a vector magnitude circuit. If I say x is equal to 0, then IW is equal to under root of y square. That is the absolute value of Iy also. This way also you can get a absolute circuit. Absolute value circuit. Now comes to the current mode 4-quadrant CMOS analog multiplier with the low power. What is 4-quadrant? Basically, if I'm going to say about the Vx and Vy having any polarity, okay. So we are talking about the multiplier circuit. Okay. I'm thinking to not to explain this thing because it requires somewhat more calculation. I need to put it here. Then I need to explain this thing. So for the time being, I'm just putting it off now today. So anybody having any kind of a query regarding exam and all, then you may ask me, because this further required some kind of a calculation to be put it here. Still, it is not yet completed totally all the things. Yeah, class, do you have any kind of a query regarding exam and all? Then I can tell you what is the issue and all the things is there. So basically, just anyone just inform me that everyone is knowing about this thing, that this subject, that is the design of a current mode circuit, is only for the internship students. Everyone knows? Divyans, Jatin, Dhanraj.
Yes, sir.
So everyone knows this thing now, right? Design of current mode circuit is for only the internship students,
Yes,
right?
sir. Hmm.
Okay, good. So I have already shared the PPT. So somebody was saying about that the issue is with the company laptop, and then for that thing, you may install the team in your mobile and you get through that one. Today I'm going to add all the emails which I have already got in the WhatsApp. So I think that will be very easy. I already have given that the ID as well, the password of that one, passcode for that team. I think that is more than enough. And for the particularly about this particular subject, you won't get in a one particular book. You need to find out different book like if I'm going to say in the first unit, it is not there in the Thomasy. So that you need to prefer the local means which you have already gone through the previous semester, means not previous semester, I will say in the previous years and all. That is basically from the analog circuit. You can look into that one. And for this, basically from second unit onwards, you need to look into the Thomasy, which I have already given in this. I think I have not shared that this thing. Syllabus. I will share the syllabus in that one. There's book names is book, not book name. That is the reference book is there. Okay, you can go and look into that thing for the more explanation. Go into that one. Otherwise, whatever I am teaching, that is more than enough, and whatever I am providing in the WhatsApp group, that is more sufficient for you. And rather going into the more calculation, but I'm not given the whole calculation for which we have already seen in the translinear circuits. I'm not given all the calculation for one of the example I have given. So for the other things, I've already designed that loops and all. You can go and look for the KVL equation with for the particular loops and write out that equation, and final equation already given in that things. So that is all for the today's class. So,
Thank you, sir.
Thank you, sir.
okay,
Thank you, sir.
fine.
Thank you, sir.